Let's now turn our attention to a very famous example in the field of photonics of a structure that has continuous translational symmetry, namely that of a slab waveguide. So slab waveguide is basically a slab of high index material, so refractive index N1, which is much higher than the refractive indices that we have for the cladding, which could be in general two different materials, N2 and N3. So let's draw our coordinate system here. So let's call this direction the Z direction, that's the Y direction, and the transverse direction, the X direction. So pause the video, and knowing what you know about symmetry in systems like this, try and figure out what a possible general formulation is of the fields that can exist in a structure like this. In this case, we have continuous translational symmetry both in the Z direction and in the Y direction. So from the previous videos, we know that in terms of Z dependence, that means that we have something like exponential minus j kz z. And then we also have something similar for the Y direction. Sorry, the Y direction. So that's the Z and the Y direction. And then, of course, there's also something involving the X direction. But for the time being, we don't really know a lot about that yet. So in terms of continuous translational symmetry, we can make statements about what's happening as a function of X and Y. So just like we did already earlier, we can use this ky and this kz as some sort of labels to label our mode. So we can classify all the different solutions by looking at the propagation constant k, which is of course ky 1y plus kz 1z, and then use these guys as a label. So drawing your attention to the small subtle detail here is that we're not labeling our functions with the eigenvalues directly, which would be these exponentials, but rather with these constants within these exponentials. Okay, some minor thing. Right. So again, we haven't touched Maxwell at all, but just based on the symmetry, we know that we have this plane wave-like behavior in the Y and in the Z direction. We don't know anything about this h of x, unless perhaps in the very special case where N2 and N3 are the same. And then we have inversion symmetry, and then we have again even and odd modes. But in general, in order to figure out what h of x is, we need Maxwell. And of course, we also need Maxwell to figure out what the relationship is between frequency that we're working at and the k values that we have here. So Maxwell, luckily, is still not that. I mean, Maxwell is dead, but his equations are still very much relevant. Okay, so let's take Maxwell's equations and let's solve those, perhaps numerically. Doesn't really matter for our purposes here. And let's try and make an inventory of all the different solutions that we have. So for example, we solve at a certain frequency and we see what are the different k values that can exist. And then we can plot them in a diagram. So we can plot, for example, as a function of the k values that we have, the different frequencies that can exist. So in this diagram here, we have information about both the spatial behavior of the solution and the temporal behavior of the solution. Because remember, k is inversely proportional to wavelength, at least in free space. So this is the spatial dimension. And then omega is inversely proportional to the period. So this is the temporal dimension. So a diagram like this relates space to time. Let's just say that every time we find a solution, we indicate it with a dot in this diagram, and then we just do that for different k values or for different frequencies, and then we just join all the dots. What we then observe is that some of these solutions will tend to cluster in lines like this, and actually they are in between a certain number of straight lines like this. So solutions like this, which appear in bands, we can call them bands. By the way, this is also why this is called a band diagram. So that's one type of solution. But then we also observe that over here, we have a continuous region where every point that you pick here is a solution to Maxwell's equations. So this diagram over here, this band diagram, some people also typically in engineering contexts, they don't plot it like this. They don't plot omega versus k. Rather what they plot is the effective refractive index, so n effective versus omega. So they flip things around and they invert some variables. And a diagram like this is then called a dispersion diagram. So be aware that you can also encounter these. They represent the same information, but in a different way. Okay, so we have two different types of solutions here, this discrete types of solutions over here and this continuous type of solutions over there. And our goal for the next two videos is try and get some more insights into these guys over here, which will turn out to be the guided modes, and these guides over there, which will turn out to be the radiation modes, so where they appear from and why they are discrete versus continuous and what the physics is behind them. But that's for the next videos. But before we go there, a final piece of terminology here. The line that separates these discrete solutions from the continuous solutions over there is called the light line. So this is also a term that you can encounter in the literature.